Okay, so welcome everyone to our second lecture in the series by Professor Marc Timme. So yesterday we were introduced to basic notions of stability and network topology and their relation, their interplay with a problem in which we knew the topology and we saw the effect on the dynamics. And today I think, as the title suggests, it's going to be the inverse problem. So I'll leave it to Professor Timme to elaborate. Thank you.
Yeah, thank you very much again for having me. As Sarah mentioned, we yesterday found that the topology influences the dynamics, which is not surprising. Like who interacts with whom in a complex network determines part of the fate of the dynamics of the system. But we also found that that and how changes in the topology influence the dynamics, so modify the dynamics. And yesterday we found that we changed it. Well, you can argue slightly because we only added a link, but if you think of parameter space, we switched the link strength between two existing nodes from 0 to essentially 1 to some macroscopic quantity. And so in parameter space, that is a big change. Typically also, one could consider small changes and ask for a continuous so typically you have a continuous dependence of the resulting dynamics as a function of topology or in general parameters, and the coupling strengths are important parameters. If you have a network of n units, you have of the order of n squared parameters already only for the coupling, and then there might be intrinsic system parameters which determine like the features of the individual node dynamics and so on. The work today is grown out of work with José Casadiego and others. In particular, we have been collaborating and still want to continue to collaborate with Monitsan, who is now tenure-track professor at Hebrew University, Hauke Hähne, who was a student first with us and then with Joachim Peinke in Oldenburg, and Georg Börner, who is currently a PhD student with us. So each of the lectures will have a slightly different focus, and the second, today's lecture, and the third, next week's lecture, will focus on inverse problems almost exclusively. The idea here is, as I mentioned yesterday, to reverse the scope, to try to get information about the topology from the dynamics by knowing that changes in the topology change the dynamics. So a standard view is the opposite. A standard view is to have a system, then you do a model of a system. You have your system model, and then, for example, you may have driving signals, and you want, or not, and you want to predict the dynamics. So if you have driving signals, the resulting dynamics looks somehow differently. But the idea is, okay, you know the model, you know possibly the input, or you don't have input, and you want to know the dynamics. So it's from left to right in this picture. You have model constituents, and I always or mostly think in terms of ordinary differential equations. So you have a set of differential equations. Maybe you have an autonomous external signal or several signals if you have a network, and you want to predict how the system collectively behaves as a function of the signal or some parameters and so on. Yesterday we have seen very simple one-dimensional examples. When we were looking for fixed points, stability properties of the fixed points. Response functions could be typical questions quantities of interest you're asking for. Response functions are quantifying what comes out of the system, given a system, and depending on the input. Like, for example, depending on the amplitude of the input, if you have sinusoidal input, you change the amplitude, you want to predict how the system reacts. And in lowest order, if you have sinusoidal input, you also have sinusoidal output if you are sitting near a stable fixed point originally. I will actually discuss that in the last lecture, which is in, I think, 2.5 weeks or 2 weeks from now. Yesterday, we also discussed bifurcations. So typically, for most parameters, smooth changes in the input, for example, the input amplitude, or smooth changes in the, like small changes in the parameters of the system result in small changes of the resulting dynamics. That's also true in systems which are not driven. You change the parameter slightly and typically you change the dynamics slightly. But if at some points and some certain parameters, for example, intrinsic parameters or driving amplitudes, you can have bifurcations, as we saw yesterday in a one-dimensional example. Bifurcations mark qualitative changes in the dynamics. For example, as I'll present in the last lecture, if you cross the input coupling strength, the strength of the input driving signal, if it's too large, then, and you are sitting originally near a stable fixed point, you will respond first for small coupling, you will respond, for small driving amplitude, you will respond locally to your original fixed point, you will stay near that fixed point, and slowly drift away with increasing coupling strengths, typically. And at some point, your drift is so too far, so you will actually leave the local neighborhood of the fixed point. And this is because the system, if it's a nonlinear system, can exhibit multi-stability, so several options of qualitatively different system states. So how to obtain a model? So far we have given a system model and an input, and we want to, given this model and input, we want to predict the dynamics. That's a forward problem. How to obtain such a model? There are essentially two methods, and now I like you to keep very close attention because it's super important, like conceptually. You either take it from the literature, so you take a model like the Kuramoto model or anything else from the literature, and maybe you want to modify it, you invent it yourself, but you take an existing model and modify that or not, and ask for certain properties of the dynamics. So this is a way to obtain the model. And the second is do it yourself. Like you're given a system, but you need a model. You need to create that. And a basic way of creating it is use the data you get from the system. You measure something from a given system, and you want to obtain a model from it, or features of the model, properties of the model. For this kind of inverse problems, Jose and I have written a review article, which meanwhile is more than 8 years old, 9 years old, which introduces the topic from the perspective of ordinary differential equations, which are typically nonlinear and which are networked. Yeah, so the very basics of that. And so in an inverse problem, you are possibly given the input. So you have a given system, and maybe you know the input because you drive your system, for example, a neural network or an engineered electric circuit or whatever, and you can observe how the system reacts. But the system itself, it's in a black box, or here it's a blue box. Okay, so you don't know what is in the blue box. And from varying, for example, the inputs, or getting different initial conditions, observations, and so on, you want to infer properties of what is in the box. So you later get the system model. So from observed dynamics, you deduce system constituents or properties of them. By the way, again, the same as yesterday. I strongly encourage you to ask questions if you want to. If you don't understand any aspect or have a conceptual question, or I should go back a slide or slow down or anything else, just ask a question, raise your hand and speak to the mic. So now we're talking about network dynamics. So that means that in the box, we know some kind of network. But what is a network? Network is a system of coupled variables in the simplest case. And you want to deduce then network constituents. What are network constituents? You can say, okay, maybe I want to understand properties of the system here. What are obvious things? What features of a network are most essential? And you can more or less see it yourself. I mean, what do you see here is I see a number of nodes and I see interaction patterns among the nodes. And of course, in reality, an interaction, each node comes with a local dynamics, possibly. If you isolate a given unit of a network, it may have its own dynamics. So you want to figure out that, or you want to figure out the coupling functions of that interactions here. But before that, even less information, even more qualitative information is much more basic stuff. First is network size, like how many variables do you actually have? How many nodes do you have, or variables? And we have addressed that in a paper with Hauke Heine. And the second feature is interaction topology. Who interacts with whom? Like only the structure. Forget about details of the functions. And we have addressed it in a sequence of papers. And first I will go to inferring network size, or more precisely speaking, inferring the number of variables in my black box. So imagine you have a black box, you can stick some electrodes in, but you don't know, for example, you can record from a few nodes, but you don't know how many nodes are actually in the system, how many variables the system has.
Just a question.
Yes.
Are we assuming that what's sitting in the black box, or the blue box in this case, is an ordinary differential equation, or can it be anything else? Can it be like a stochastic?
So conceptually, it can be anything. What I will present is for ordinary differential equations, but what in the later part will become clear that it depends on the flow. You need to understand properties of the flow.
Okay. All right.
So that's one reason why I yesterday introduced the flow, because the flow somehow covers all kinds of system descriptions.
Sure. Thank you.
It will become clear very soon. I actually start with, I basically do linear algebra in the next half an hour or so. By the way, today's talk will be much shorter than yesterday's. It will probably be a bit above an hour, like 1:15 or something. So not to overcrowd everyone. Okay, so the blue box is now like this. And I assume, so there's some network in here. And of course, we don't know anything, right? We don't know anything of the network. And we assume that what we can observe is the dynamics of the given nodes, okay, the colored nodes. All the other nodes, we don't even know that they exist. And we want to find how many total nodes are there, okay? How many variables are in the system. So you can perceive the dynamics of n units, small n, and I have two n's now. One is small n, which is the number of units you can record from, you can observe from the dynamics. And there's capital N, which is the number of units total in the box. And capital N is what we are looking for. And there might be inputs. And as I mentioned yesterday, a simple input is just a delta kick. So at some instant of time, I kick the box, and then the state changes away from a fixed point, for example, or away from any other point. And so I see some relaxation dynamics or some other types of stuff. And I kick it again, say in a random way. So I don't know actually what is happening, but I know it's not in its final static state or stationary state. The description or formulas I use here are x of t, which is the state vector of the entire thing in the box. And I don't know x, because x is just a collection of all the component states, which I can't see. I can see the state vector of the perceived units, okay, the colored guys, and these I call y of t. And so obviously x of t is an extension of y of t with several components xn, or x whatever m, I can't observe. And the basic question is, what is the number of variables? Like, how what is the dimensionality of X given I can observe Y? And it's very curious because imagine you have a black box, you have like of the order of 100 variables in there, like 100 nodes, for example, and you can observe 30 of them. Was it echo or was it a question?
We're fixing microphones, that's it, sorry.
Okay, so assume you have of the order of 100 variables or 100 nodes in the network, but you in the system, but you don't know it. You only can record from 42 of them. And after recording sufficiently many times, like from different inputs or different initial conditions or whatever, I tell you, oh, there are 112 nodes in the system, or 112 variables. Wouldn't you be surprised? Like, you do a measurement, you measure according to my rules, you measure something, you give me the data of your measurement of 42 variables, and I tell you the system you're measuring from has 112 variables. It's somehow surprising, right? At least I found it surprising. And the idea is like this. The idea is basic, but still non-trivial. The fact that it's basic leads to the constraints that, or to the insight that it's also general, because it doesn't make much assumptions. Okay, again, we can record from a subset of variables. And I interchange variables and nodes because all the examples I show until some time later are one-dimensional units, okay? And later I'll go to explain what happens if we have higher dimensional units. So you start with one initial condition. You can record from your 5 units. You get time series. And actually, if you are really an experimenter, you can't get continuous time series, but you sample them at discrete times. And then you kick the system again. You started from additional initial condition with but the same system. You measure again, and then you collect the data in a clever way, which I'll explain in the next slides. And you collect these into a matrix, and the matrix becomes bigger and bigger. And what happens is that the rank of that matrix is naturally bounded by n, the number of total variables, because you can't have more than n linearly independent vectors if you only have n degrees of freedom, right? So that's a rough idea. You throw in more and more data into your matrix, and you measure the rank. And once the rank stops increasing, you have found your network size. That's a basic idea, and it's very, very simple. Yeah, and that's all we do, right? So we collect different sample trajectories of perceptible states. You suitably arrange those data into what we call a detection matrix T. Like this is all data you have.
Yeah, my question was, so no matter what, we're always going to get the same big N for any given system, or can this procedure give us like different sizes depending on what the input that we're putting in?
So the goal function, the goal we have is to, if you have exactly n variables in your system, we actually give you back n. So you do the measurement, you say, okay, here are my 42 trajectories, repeated measurements, give me all the data. We crunch the data and we give you back 112 because you have 112 in there. That's the goal, okay? It doesn't always work. There are certain constraints, and it's also not all constraints are well known today. I'm just presenting the idea, but it should be that if you have 112 variables in your system, you should get out 112. One obvious constraint is if, for example, say that several of the unobserved nodes have identical dynamics, so you can't distinguish them, and they're coupled identically to the rest of the network. If that is true, there's no way to distinguish them. So you would discount certain variables. So you can't count dependent variables as independent by mathematical construction. But apart from that, it should in principle always be possible. Practically, it's very hard, as I'll show you. Is that answering your question?
Yeah, okay.
Thank you.
May I ask a continuation of that question?
Of course.
So you basically, you need to excite all the possible modes, right, in order to collect the information. The question is, how many input nodes do you need to have in order to be sure that you can excite all the modes?
Everything I present today is just starting from different initial conditions. So I don't have input nodes, but recorded nodes. You're probably asking for like how many colored guys I need.
No, basically, how do you kick the box? That's the question. So if you can prepare it in different initial conditions and you can cover all possible modes, that solves the question.
True.
But if the only way to prepare a new initial condition is to provide a kick, you do need to consider some sort of input information in terms of the kick and how many nodes it can excite.
Exactly. If you have a lower dimension, so say you're staying at a stable fixed point, and you have a lower dimensional excitation which doesn't excite all possible variables, then you, by construction, you can't see them. Right? There's no way to find out. And so in this sense, you're right that you can only see excited modes. So what we call active variables. The general idea is like, say you have physically an experiment, which is physically in the box, and you actually kick the box, like I kick it with my foot, okay? Then the typical perturbation is like random. You would randomly change the initial condition in some way, and typically you affect all variables. Of course, not true. That's true for a mechanical system. Obviously, it's not true for electronic systems. But you're completely right. If we need to activate all variables, or more precisely speaking, what you measure in the ideal case is all activated variables, all relevant variables. If you have, for example, identically synchronized variables, you will not be able to dissolve it because they are 100% dependent. So there's no way an outsider can say. It's just an information theoretical concept. Is that? Do you agree, or is that answering?
Yeah, but no, I totally agree with the mechanical analogy. I had in mind exactly some electrical chains. So I was thinking of how do you excite things? You need some input modes where you put some voltage, etc., etc.
Yeah, but say you have a complicated electrical circuit, yeah? And now what you could do from the outside is take a somehow random electromagnetic field and just push it, kick it to the system. Then you would generically excite all variables. It might be, of course, that the parameters are such that some are much less excited than others and so on. There might also be noise issues and so on. That's all technical, but mathematically, you would generically, typically, except for parameter set 0, almost always excite all variables. And if you don't, you only measure the excited ones. Okay, I continue. Yeah, should I? Yeah. So we suitably arrange these in a detection matrix. We increase the size of the detection matrix until the rank leveled off at ideally at n. Why n? Because that is the largest possible rank. So the rank of a matrix is at most the number of potentially linearly independent variables. And so now the entire technique is to make a few basic observations and to, like, this is mathematical and the other one is technical in the sense that we have to arrange in a sufficiently clever way to exploit that. Okay, so the simplest setting is super simple. It is a linear system and capital N dimensional. It is noiseless and relaxes towards a stable fixed point. So you have a fixed point, it's stable in a linear system, You kick the system to random initial condition and you observe the relaxation. And everything is linear, so you can even analytically solve it if you want, if you knew the model. And I'll use that to present the idea, okay? That's the basic of what's going on. So you have a nonlinear system, you linearize it. The deviation to an existing fixed point we call x. For the new variable x, you get a linear system, or you just start out with a linear system in the first place. If you start with a nonlinear system, these aij's are given by the partial derivatives of f. So aij is dfi dxj evaluated at the fixed point. If you have a linear system to start with, A is just given you whatever you give me the matrix. There's also some constraints in terms of how information can flow through the network. Like A can be interpreted as a weighted adjacency matrix, so it tells you how who is coupling to whom. And of course, if there are two nodes which don't feel each other, even not indirectly, then there's no way we can figure out that node, right? So if you have, for example, a very simple network of 3 nodes, you have a coupling here, and a coupling there, but you measure from that one, you can never find any influence from these, right? Because you can't see them. So there are certain constraints of it, and if you want to avoid discussing it, one simple class, an important class of networks is just strongly connected networks. So everyone is communicating with everyone else. This helps you identifying that. There's also some constraints on observability, but I don't discuss it. There's an extra separate PRL by Porphyry following ours, relating the observability of to the reconstructability problem. Okay, so you have this linear differential equation because it's linear, you can formally write down a mathematically analytical solution. X of t is matrix exponential function E of exponential AT. Do you know that? This is also, it's defined in terms of a Taylor series expansion. So a series power expansion, power terms of AT, like the normal exponential function for scalars, and then the resulting object here is also a matrix. So x of t is some matrix which is given by A and time t times x of 0, which is the initial vector. Now the problem is you don't know f, you don't know the system, right? We have no clue what f is, so you also have no clue what A is. And because you don't know A, you also don't know e to the AT. But what we do know is that if there's any A, this is the solution, okay? A bit tricky to think about. We factually, as an experimenter, we do not know F or A. But if you do know A, we know how to write down a formal solution. It's like this. So the observed time series is a projection of the full time series. X of t, you project out the first, we label the nodes such that these are the first small n variables. So again, capital N in our example was 112, small n was 42. So this is the 42 by 42 identity matrix, and the rest of the matrix is just full of zeros, which just projects out the relevant variables. All others are 0. So this is an n-dimensional, small n-dimensional vector. This is a capital n-dimensional vector.
I'm sorry. I have a small question concerning the time series.
Yes. Go ahead.
She overpressed on the speaker button.
What should be the sampling rate? Is there a specific value where the sampling rate is that our approach is not valuable?
Very, very good question. It is not fully answered. I will go briefly to this question, and it's already for a simple setting, it's very complicated. And so that's actually a research question to investigate how the sampling rate plays a role in general. We have now some statements which are observations, as a function of stability of the fixed point, and for a special case which I will not reveal before I show it. So please wait a bit and I'll show you some example where sampling rate is important. There are three entities now. Is that raining? Is it raining in Dresden or in Beirut?
Not here because we're also underground.
Oh, yes. Crazy. Okay, I should have come to Beirut.
Yeah, it's a shame.
So is that noise level is okay because it's raining to a metal plate here?
No, the sound is very good. We don't hear the noise.
So you have this y, and now that's a projection of this. So this you can rewrite this each component of y as a sum over variable theta ij of t times the j's component of the initial vector x of t. And theta ij is now just an abbreviation of this time evolution operator. Okay. So remember that this x of t is the flow. So in other words, the flow is represented by matrix multiplication here. The flow itself is also, well, it's just this matrix exponential. And we actually don't need this. We know that it's like this, but we only need this form, okay? We only need the fact that yi of t is written as a sum over time-weighted functions of I and j and sum over all j. So what we do now, we observe capital M different time series. So from M different initial conditions, for example. We have small n perceptible units, and the other units n plus 1 to capital N are not perceptible. So these are represented in this by the 0 here. And we do that for k different time points. It's not trivial how to combine k and m to relate to make it sufficient to get a faithful reconstruction. Okay, this is just copied over.
Do you mind going back to the slide before, because we had somewhat the last lines cut off. So we just fixed it, so we couldn't see.
Okay,
So
capital M time series, different experiments with the same system, small n observed units, and the n plus first to capital N's not perceived, and k different time points, okay? T1 to tk. That's the sampling in time. And we will need these three numbers soon again. And that's why I just copy this one with that information over here, okay? Now I have a problem because I don't see my own slide. Okay. So we arrange the time series into a detection matrix. How do we do that? First of all, you fix small m. This small m labels the experiment. Like the fifth experiment is like this. You get a following trajectory as a function of time, and you represent this theta ij is also a matrix, okay? For the vector xm. Problem here, note what the actual problem is. Theta of t is a time evolution, which is determined by the system which we do not know. xm is the full state vector of all the components, which, because we can't observe all the components, we also don't know. So the right-hand side, essentially, we don't know. We know some of the components of x, which are the observed ones, but the others we don't, and the time evolution we also don't. So essentially, here's is something which we have no clue of, zero clue, okay? But we do know that this relation holds, okay? And that's a conceptual, like, a step. We do know that relation holds as a function of time for a given m. Now we do that for different m's, from 1 to capital M. Actually, we take into account into our consideration more and more experiments. And now we collect all of these. We collect y1 of t is this quantity, a vector, a vector, a vector, m of these vectors, and we get an r n cross m matrix, which in addition depends on time. Okay, that's a time-dependent matrix, size small n times capital M. We know that this quantity, this matrix, time-dependent matrix, can also be written with the same, and now it's a catch, okay, with the same time evolution operator, because it's the same system. There's the same theta of t times x0. So we just write this collection for different m's as this matrix equation. Now this is the matrix, this is the matrix, and x0 is a collection of different initial conditions. Okay, this is an n-dimensional initial condition collected m times. Now you sample them at different, you don't record all the times, but you only record at certain time points. And then we take these matrices and put them into what we call a detection matrix. And we do it in this weird way, but just to represent it in a simple way. So it's the transpose of this guy and then transpose everything over. So essentially it's a way of writing it. So the detection matrix is this T, which is now containing all information available. We have all of our M experiments. We have K time steps for each. And we have collected everything we have measured into T. At the same time, we have no clue whatsoever theta K is. Theta K is a matrix evaluated at different times. It's this matrix, the same time evolution matrix evaluated at different times. Therefore, it's important that across different experiments, you measure at the same times. Like if you, for example, if you measure in 1 second intervals, you want to do that again in the next time. If you don't do that, but measure in intervals of pi seconds, you have a problem because you can't write it like this. So this T contains all information available. And again, T is known completely. All the measured data are in here. Theta K is the time evolution of your system, which we don't know. And x0 is essentially also unknown up to some small n entries. Like if this is a gigantic matrix, capital N times capital M, and only the first small n entries, like 42 out of 112, are actually known. But we know that we can write like that. Okay. It's also important to note that the dimension of T obviously does not depend on capital N. Otherwise, it would be trivial, right? We would put in information about the system size already, but it's not. It's like a Kn times M matrix, and the N is in the middle. Like the dimensionality N is given by the size, by the number of rows of this matrix, or number of columns of this matrix. So N is is disappeared in this matrix multiplication. And we deduce the network size from this one matrix. So we have a matrix equation where we only know one side, and we want to know properties of it. And the only thing we now use, mathematically speaking, is that the rank of T is smaller or equal to the minimum of the ranks of the two other matrices, because it's the product of two matrices. So if any rank of the two matrices is smaller than capital N, the total will be smaller than capital N. And the rank of...
I'm sorry.
Yeah.
Can we repeat exactly how we're stacking each big Y into big T?
Yes. First, you collect for a given M, you write it down like that. That's just this one written out as a vector for given initial conditions. Then you do that across different initial conditions from 1 to capital M, and collect them in a matrix Y, which just collects the vectors Ym. Now you put these, and this is now a matrix with this matrix equation. Importantly, so this works, this is exactly the same theta as this one, because we are talking about the same system, right? If you would modify the system each time, you would have had different zetas, system dependent. But we don't. We have the same system, so this zeta is the same. Now we collect these matrices y of t in this way. Okay?
So we're like essentially stacking the matrices on top of each other.
Yes.
Okay.
So it's not hard at all. So it's just that you have to take care that you write it down properly and you use everything you have, right? So the task is now to deduce the network size from T. And the idea is to exploit the rank inequality, which is generally true for just one A. You have any matrix A. Should I call it A? I'm out of letters. You have a matrix B, which is a matrix C times a matrix D. And the rank of B is always smaller than the rank of C. No. Rank of C and the rank of D, okay? So this is the only thing we use. It's the basic linear algebra fact. Interestingly, one of the referees of the paper was criticizing that, oh, that's so simple. Why do you want a high quality paper out with this simple linear algebra? Everyone knows that. And we were essentially replying, yes, that's the point, because we have a very basic rule, but no one so far could actually tell me the state-based dimension. And we just map that to an appropriate collection of data. So that's here you again can see that the n is somehow in the middle. That's why capital N doesn't appear anymore. You now evaluate an increasing number of trajectories taken into account into your T. Okay, you put some number like 44 trajectories in there. You measure the rank. You increase it to 44. You measure the rank. You increase to 45. You measure the rank of T. And what you expect is that the rank grows. Okay, because if there are 3 active variables which you haven't seen, the rank of that one will grow. At some point, it will saturate, and the idea is that at some point is capital N. And now this is rescaled. You divide m by n, and the estimator as a function of m trajectories taken into account as a function of n, divided by n, and do that for, well, here's 3 different n, and you see that it actually levels off exactly at m equals n. But this, remember, is for a very, very basic, noiseless, linear system with a stable fixed point. So in other words, if you take 150 measurements and they are all linearly independent, well, the trajectories, the recorded data, then you get 150. If you have a system of 50, you get 50. This is now for linearized phase oscillator systems. So I mentioned the Kuramoto model yesterday. This is actually a near phase lock state of a Kuramoto model. So it's not exactly linear, but it's a sine function, but we linearize it and use the same thing. And you see some deviations here in the slope, but the point is once it saturates, you are safe. You read off your actual n not from this axis, but from that axis where it saturates. There are lots of technicalities in a real problem if you actually want to do that. And the first thing we did was detect the rank by detecting the largest gap in the singular value spectrum. And for the linear system, it looked like this. I think I hear myself. Maybe. the ordered singular value spectrum is decreasing, and at some point it's dropping to essentially numerically 0. And so the big gap, and this was done for a system of size n, capital N equals 100. So 100 node in there. How does it look like? And it looks like this. Of course, if you have inexact equations, for example, if you have a nonlinear system or noise or anything like that, or strong heterogeneities, you get less exact predictions because everything builds on linearization. So this is the same for phase locking of Kuromoto model. They are different. There's still a gap, so you're still predicting the correct network size, which is n equals 100.
Mark, I have a question. So if you don't have the privilege of carrying out experiments, and you have a very long time series, can you sample like multiple intervals from the series and consider them as kind of different experiments?
Mathematically, in principle, yes. Factually, it depends, because it depends on what kind of time series it is. For example, if it relaxes back to a fixed point and you take very late pieces of the trajectory, they are already very close to the fixed point. So they essentially are not linearly independent anymore unless you have super high resolution.
Right.
So it's actually a precision problem in some sense. If you had arbitrary, like mathematically, if you had arbitrary precision, that would perfectly well fit. If you don't have arbitrary precision, which is a typical case, then you have a problem in reality, in practice. You can trade, like if you need two kinds of high performance here. One is the precision of your measurement, and the second is the precision of how you determine properties of the matrix, like the rank. How stable is the rank detector for a high-dimensional system? If you have linearly independent, but almost linearly dependent vectors in there. That's one of the problems.
And just a question which might not be related, but this kind of procedure of looking at the gap in singular value reminded me of, I don't know if this DMD, like this decomposition where you stack the time series and delayed versions of the time series, and then you apply a singular value. So you kind of beef up your observation matrix or your T matrix in a way. And then look at
delayed version of this. What do you mean by delayed versions?
So instead of X of T, you start stacking, let's say from X from 1 to T, then from 2 to T minus or T plus 1, and then so some sort of delays over.
If you have many a lot of data, this might help, but the first thing you need to fulfill is to have really independent data. We didn't try that, but in principle that should be feasible with the same technical constraints. Okay, so linear system, nonlinear system. Now everything we did is near a given stable fixed point. Well, here is a fixed point, here is a stable periodic orbit, but essentially in a co-rotating frame, like if you take the oscillators and move with them, it is again a fixed point. And in typical cases, you don't necessarily reside near a fixed point. Okay, so the question is, how can we go to non-fixed points? And now we do a small generalization. Go to a nonlinear system and not near a stable fixed point. In the simplest setting, take an arbitrary point in state space, Z, which is a full state space again. Remember, Z dot equals f of Z. You don't know f, you don't even know Z, but you assume there's something Z. Assume there's some state in your state space, and you sample trajectories which in your state space are somehow nearby. And under for certain types of experiments, that might be true. So the question is what to do with these data if you're not near a fixed point. And so Z, again, need not be a fixed point, just any point where you have, with property that you have sufficiently many data near it. Of course, you can never know whether that's really true because you can't measure certain components. You can only measure some components. But if it's true, the following holds. You measure sufficiently many trajectories nearby that point. And then you approximate the flow. You know that the flow and z of 0 is some initial condition which is also close to z, okay, z star, state prefix. The flow is then given by phi t of z of 0. This is just some function again, because the time evolution of the system, you don't know the system, so you don't know phi, but you do know that it exists. So you can write it like that. You consider now the difference between two trajectories. One is z1, the other one is z2. And now you linearize near a point, near a time, okay, whatever the time is. You just pick some time which is appropriate given the initial condition here, such that this recorded trajectory delta z of t is nearby, well, each of the z of t is nearby the fixed point, and the difference is then nearby 0, okay? So this one is a trajectory which is close to 0 in some sense, and it needs to be in a linearized regime. So this one should be an okay approximation for phi in this piece of state space. Then you can write y as a projection, as before, as a projection of the first n variables of delta z. And now you get the same form as before. You can write the component of y as a sum over theta ij times y times zj, delta zj of 0. And what you get here is a different type of theta ij, okay? But the form is the same. Theta ij isn't just this ij component of this derivative here, evaluated at a fixed point with some strange time shift. It doesn't really matter. The point is this one exists. It's the same form as it was before. And now, in addition to that one, so we go now, we use it now at points which are not fixed. One is near a periodic orbit. And we now use, as an example, we use Rössler oscillators, coupled Rössler oscillators, and we only observe one of the components of it. So Rössler oscillators are 3-dimensional units per node. And so if you have n of capital N of them, you have 3 n variables, but we disregard 2 of the variables. And here I have a disclaimer, because it doesn't work always. It works for certain variables and not for others. We have some rough ideas of why it works for some and not for others, but we have not a good understanding. So that's also a research question of how can you do that. In principle, of course, you can always view your full state space, like the 3 n-dimensional state space, as just some network with 3 n variables, where each unit also has a network of individual scalar variables. But we didn't do that yet. Although we're currently not working on that, but it's really an open problem. So periodic orbits, you perturb, it looks like this, and this is a stable periodic orbit. This is a chaotic trajectory, but on a stable chaotic attractor. So also the z variables, well, converge towards each other in the sense that state space volume compresses in this direction. And now we do the same problem and ask now as a function of small n over n, like how many units you have divided by the number of units. And it oscillates like crazy, and at some point it just saturates at n. And here the same. So this for periodic, this for chaotic. It just illustrates that in principle it's possible. It does not rely on having stable fixed point. And now you can try other things like, okay, we started with this noiseless linear system, and now we have a homogeneous system. We have a noisy, heterogeneous, and sparsely coupled network. And this is a weighted adjacency matrix. The degree of grayscale is representing the weight. So light gray is weak coupling, white is no coupling, black is strong coupling. You see that the trajectories are somehow noisy. And you also see some noise here, but you again see that it saturates off at 1. And now, of course, you ask where exactly it starts saturating off will depend, for example, on the noise level. It will also depend on the number of units you measure. And this is just 2 examples in a system of 100 where you measure 80 and 90 units, and you see that the number of experiments you need is growing from 100, which is the noiseless case, but you compensate for noise by more measurements. Unfortunately, well, the noise here is pretty low, so it's unclear what happens for large noise. It will just grow, and it will rapidly grow, apparently. So here you measure already if you measure 80% of the system with the current methods, you have to do 400 measurements and by the same scheme to get a reliable estimate of n. So in other words, when does this actually stop oscillating at a given m? And the second part is about the size inference from time series of only one variable. Okay, now just recently we had 80. Before I had this example, it was 42 out of 112. I didn't mention the real example explicitly, but what we got here is here. Oh no, it's not here. Well, no, it's not shown. In the ideal case, you can measure something like 15 or 20% of the system and get the full dimensionality. So with the current untuned method. Meaning that you have a network of 100, you measure 20 or a bit more than 20 units, you can actually tell there's 100 variables in the network. So now it's important to understand that this rank inequality doesn't care about small n. It has n in the dimensionality of these matrices, but it doesn't, the rank inequality in itself is independent of n. That's independent of how the data is assembled. That's also why you could, in principle, do that with from one trajectory. And well, one long trajectory of many components, or you could alternatively do that from trajectories of only one variable. Okay, so assume you have a network of 15 units, and you only measure one, and you want to find whether it's 15 or 14 or 12 or 10 or 20. And you actually reliably find 50 under pretty strong conditions about the precision again. So the idea is like this: instead of recording from different trajectories, we now record only from one trajectory of the same node. There's only one node, one variable which we measure, but we collect the data in exactly the same way. And then the question is, can we get capital N? So mathematically, it's clear that the state space dimension is deducible from one variable only, because it's like the same rank inequality. Practically, it's harder, and I only briefly sketch what's going on here. So these are working and non-working examples in a linear system where the eigenvalues of my given adjacency matrix are distributed like that. So it's a stable fixed point. Real parts are negative here. There's a certain gap, which here is of the order of 1, maybe 1.5 of the eigenvalues away from 0. So there's a certain robustness of the stability. And you record from this one trajectory, from one variable, you record several trajectories in different experiments collected into your matrix. And from the matrix, you get the eigen singular value spectrum, and you take the largest gap And here it turns out that, interestingly, it's exactly where it should be. I would think it's 12 here. So the inferred dimensionality is 12. You do it again in different settings, like this is a different beta, okay? This is a different kind of stability. And here you find that the largest gap is here, not down here. So you deduce, I would think, not a 10 instead of 12, although you have the same network structure with a different dynamical system because you have different beta. So all of this is technical in the sense that it depends on your precision and on your rank detection and so on. One example here is you were asking before on the number of samples, and instead I will go now to the number of time steps, which of course relates to the number of samples. Number of samples times number of time steps is the length of your trajectory you record from. And well, all of these three parameters may be or may not be relevant for certain experiments. You see here that with it varying the time step, like the spacing of your sampling, the predicted system dimension goes up, it stays up, and then it goes down. And the maximum of that is actually the correct system size. And we do it here twice, once for n equals 12, once for n equals 15. And well, it looks like it works. And then you can show how that, like, analyze, quantify, but numerically here, the probability of different realizations of networks given a beta, like a stability parameter. The larger beta, the more robustly stable it is, the more attractive the fixed point is. And the weaker, or the more strongly stable that thing is, the the lower the dimension you can faithfully reconstruct. Okay, it just moves down. But still, up to order of 10 or more, you can faithfully reconstruct system dimension.
Question, Marc.
Yes.
This idea of inferring practically n is the dimension of your system one way or the other. Has this been mapped to Takens embedding, where you're trying to find the embedding dimension of? Very
interesting question. No, it's not. Also, I think this is one of the most interesting open problems, but it's also not a trivial problem. One is because the embedding does something related to what you mentioned before, namely delayed variables. And second is what Takens embedding does is it embeds trajectories on attractors, like typically on chaotic attractors, and it asks for example, the dimension, then later can ask for the dimension of the embedded trajectory, which in itself is hard, right? We know that, right. Practically hard. And here we don't ask for the attractor dimension, but for the full system state space dimension. Yeah. It is also known that if you try Takens embedding, it ends also around somewhere 10. Like 10 is already a high number. If you manage to reconstruct a 7-dimensional chaotic attractor, you have already done an extremely good job. So it is this one, I see it as a complement. So maybe we could apply that, we didn't try, but maybe we could apply that to actually attractor trajectories and try to infer high dimensional chaos from that more reliably. We didn't try that, but that's also an open problem.
Thank you.
So more interestingly here, we did that. I mean, there's no way I can briefly explain everything here, but we did that for. So what is plotted here is the probability of success, like correct predictions, as across realizations of a network at given beta, at given type of stability, as a function of time step and number of samples. So this is now an interesting thing, because the number of time steps times the number of samples is the total length of recording. And if we ask for equiprobable lines, like this is now 95% regime, you get these weird curves. And already this is logarithmic, so somewhat weird. But if you transform that to the total time covered, so you multiply this by that and plot both of them logarithmically, what you see is it's essentially independent of the time step and only dependent on the time, the absolute time. So this is just the same data transformed, okay? Blue is 5%, so it's like the rest regime here. Now you increase the stability, and what happens? It changes. So although this somehow looks similar to this, it is actually changing the boundaries. So here in the intermediate stability regime, one of the boundaries is staying, is becoming vertical, whereas the other one is horizontal. And now you increase stability further, and both are vertical. We have not a good understanding of what's going on here. So we can, as a first approximation, we can take these as heuristic observations. We can say, okay, increase stability, make lines in this plot time step, length of time step, and total time covered. Moves the boundary, the correctness boundary, like in which regime you can actually recover. So that's also an open problem. Why that is, we know it, like for our sample model of a certain weighted random adjacency matrix with certain stability properties, we know that it scales like that. And these are like three typical examples. If you increase beta further, it will just stay like that. If you decrease beta, it will first stay like that, and then something completely different happens because the system at beta equals 0 becomes unstable and close to instability. Already stuff gets weird. Still, so that's an open problem, and there are more open problems. There's so far nothing for one variable and nonlinear systems. What we currently try is weakly coupled, very weakly coupled, non-synchronizing Kuromoto oscillators, with the purpose that somehow it's wiggling around still, so you have some linear independence of recorded trajectories. And then, of course, the question is, what is the feasible minimum n larger than 1? I mean, now, so far we were asking, what can you do with given n variables? Now you want to do n equals 1, which was presented before for linear systems. It's unclear for nonlinear. And if you say, okay, I can record from 5, how does it depend? How does it depend on the function, on these parameters, like the number of sample points, time interval, and total recording time, which of course is like t is a product of delta t times k, on parameters of the system, like the stability properties or instability properties, if you talk about, for example, chaotic trajectories, and on the nonlinearity. In principle, it should all work if you have sufficiently many data with sufficiently high resolution near any point, like the original work by Haukein. But how that actually works and why and how it changes is so far unknown. There's now a second part, and I would probably defer that to next week, because my fourth lecture is relatively short, like this might be like half an hour, and I have still a lot of material to cover on the inverse problems, and we could just continue next Tuesday, that is, if you want. That's up to you. Otherwise, it will be another maybe half an hour or more.
Yeah, I guess we can pick up the continuation of just for them to kind of digest this and play around with it. Okay, I guess that's kind of
Yeah, that's nice. Okay, and it's also more natural because after that we'll have a first reconstruction of topology from continuous time series, from ordinary differential equations, and next up is reconstruction of topology from discrete times, like if not maps, but hybrid systems. So, for example, neural systems where we only record the event times of neurons.
Yeah, perfect.
I'd like to ask a question.
Yes, please.
Could you please give an example where determining the exact network size is important?
Oh, if you want to have a model of anything, so if you are for example, a biophysicist or a mathematical modeler in biology, and you want to understand your gene regulatory network, one open question is how to actually find the full network. And the basic thing, first thing you need to know is the number of variables. Did you miss any variables? What biologists or biophysicists typically do is they measure individual nodes, essentially. They measure quantities, concentration of stuff they know, and then they measure connectivity, like who is influencing whom individually. And there's no good model of, no good procedure of how to systematically expand that. That's one example.
Oh, thank you.
I also have a question. We didn't touch still upon the topology, so how the nodes are connected. And I was wondering, is there a better choice for the visible degrees of freedom? So if the visible degrees of freedom are, like strongly connected or not, like does this influence like the convergence? Yes.
So if you want to ensure that it works, so strongly connected is mathematically a sufficient condition. Doesn't mean it always works in practice, but if it's strongly connected, there's a chance you can make it. If it's not strongly connected, it depends on which nodes you measure, whether you can actually get the influence of all the nodes, all the variables in your system through directed paths through nodes you measure. Let me give an example. So say you measure a collection of nodes here. They might be connected like that. And there's a part of the network here, which also is somehow connected. If it's like that, that should be fine. Like if here, this is a strongly connected component, for example, and they influence this one is also a strongly connected component, and you record from these, right? Then you should be okay. But obviously, if you have another component which is fed by that one and there's no connection either back to this or to the final component you're recording from, then there's no way you can detect any of these nodes, right? So you need the condition that there is a directed path from all variables you want to see to the variable, to at least one variable you do observe. So strong connectivity is sufficient. Weak connectivity, strong connectivity means if it's strongly connected, you can use all, in principle, use all nodes for recording. If it's weakly connected, you have to take care which, and not strongly connected, you have to take care which units you record from.
Thanks.
Another question, if I may. Are there any difficulties, conceptual or technical, if the number of modes becomes really very large, like in thousands of
Yes.
millions?
Yes. There are technical difficulties. And one is well known in numerical linear algebra. It's just determining a rank of a matrix with entries that are almost linearly dependent. So almost you can quantify that, for example, by the scalar product of any pair of vectors. If the scalar product is large, you typically run into problems. And similar things actually happen with the reconstruction of other features like the topology. I won't present that next week, but the first work I did on network inference used random initial conditions, which essentially led to random trajectories, or random, well, as good as random vectors in state space as trajectories. And this led to matrices which didn't have, they were formally, mathematically, were linearly independent, but formally they were so close to dependent that the determinant, even at moderate sizes, was like 10 to the minus 40. Okay, so there's nothing to distinguish from zero in practice. Mathematically, it's one story, and the other story is whether it's practically feasible. If you can ensure that you find the rank properly, I would think you can do. I mean, you have to have a lot of precision in the data and so on, but if the precision is good and your rank finder is doing fine, then you are in business. These are the two constraints, bottlenecks say.
Okay, if our audience from Zoom don't have any questions, I guess none of us here have, and I guess we can call it a day, and thank you so much. And
Thank you very much.
we'll hope to see you all on Tuesday for the continuation of the series on the inference of topology now. That's the prelim for what we did today, is to actually know how many interacting components there are for us to actually infer the topology of that. So that will be continued on Tuesday, and then we'll break for a week, I guess, and we'll meet on the 23rd, and that's going to be our last lecture. So
thank you. Great. Have a good weekend, everyone.
You too. Enjoy the weekend.
Thank you.
Thank you so much. Bye-bye.
Bye.